We are moving to the next session, the last session before lunch. So still 4 amazing talks. We have 1 invited talk and 3 paper talks for this session. So entitled Physics for Imaging, very tied to the topic of computation imaging community. So the first talk we are going to have the invited talk, physically grounded generative imaging. So the speaker is actually Nian Li, on behalf of Jing Yu. I guess she can tell you more about this. So yeah, let's welcome.
Thanks, Evan, and good morning, everyone. I'm Nian Li. I'm an assistant professor from Clemson University, and I'm giving this presentation on behalf of my former advisor, Jing Yu, who cannot make it here today due to the time conflicts. So the title of the talk is Physical Grounded Generative Imaging. So before we start, there is an analog warning. To make the presentation smoother, so I may use some first-person pronouns which may be misleading. So if I mention I in the talk, actually it's not me, it's not Nian Yi, it means Jing Yi. And when I say we or our, that is maybe a little bit more complicated because it can be Jing Yi's group, it can be everyone, and depends on the situation. And I promise this is the only slides I added in Jing Yi's presentation. And now we can formally start like today's talk. So by ways of that background, Jing Yi has been with Shanghai Tech University for more than a decade. I was actually his last student in US, in Delaware. So in Shanghai Tech, his team has built a number of imaging systems ranging from the light field dome to an ultra-large light stage. So more impressively, Shanghai Tech students have received 14 Best Paper Award at CVPR, SIGGRAPH, WIS, MICAI, and so on. And some of you have already admitted Shanghai Tech students to your graduate program, but more are welcome. So today's talk focuses on how to bridge generation with imaging. Before we get to that, let's look at what happens to images. The key advance is that image can be mapped to features using either classic CNN or transformer. So those features can be used for downstream tasks. The same actually is happening in 3D, and the 3D representations are becoming more stochastic than deterministic. But more importantly, they are differentiable. So whether it is nerve or like 3D Gaussians. In these, one can design tailored solutions to map features to a variety of downstream tasks, from rendering to modeling and to segmentation. So one such example is 3D generation from single image. The work presented in this slide's claw is from Jing Yi's group, was the first high-quality 3D generator. It aims to map the 2D image features to 3D shape features. So I like to borrow what Jitendra says on generation. Representations are like languages or currency, and generation aims to conduct the currency exchange. However, the key is understanding why exchange rates make sense. So in CLAW, the image and the shape features are aligned by transformers, and the vector set is used as intermediate representation. And the geometry encoder can be accompanied with special decoders for understanding tasks. For example, one can embed semantic meaning to shape to support what we call the part-aware generation. So here is a very cool demo to show. Okay, by far, the generation and understanding pipelines are for RGB images, but why not extend to more imaging modality? So the first example is neural transient fields, we call the NETF, in NLOS. The NLOS aims to recover hidden scenes from time-resolved measurements or transients. And 5 years ago, we proposed to use the NETF to represent the scene. So to optimize the NETF, we employ a physics-based differentiable transients render. It is important to know that the NLOS rendering requires sampling over a hemisphere rather than a long array as in NeRF. We adopt the hierarchical sampling to concentrate computation on important waveform regions. We further resample scanning points based on their reconstruction losses, providing stronger supervision. So we have also looked at specular surface reconstruction. There, what matters the most is not the RGB color, but the normal. Therefore, we associate at each voxel the normal and the density. It works out actually amazing well. In similar vein, we have extended the NeRF model to MRI reconstruction, leading to a paradigm shift in medical imaging, where my colleague won the MICAI Best Paper Awards in 2024. So coming back to NLOS, I have talked about the neural representation. How about feature encoder and decoder for tasks such as understanding and generation? So we first contrast transverse, a large-scale synthetic NLOS data sets. It has 500,000 3D objects selected from the objectverse of different categories and materials. We rotate, translate, and scale each object within the hidden space before simulating the corresponding transients mentioned. So next, we train a masked encoding, see only parts of the transients and predicts the rest. Same as 2D, the features can be used as the numbers of the tasks. So we call the trained encoder marmots. The marmots suppose hidden scene recovery from sparse and irregularly sampled transients. It supposes a more flexible scanning patterns, which is important to real-life applications. So here we scan only a sparse subset of measures. As the masking ratio increase, direct reconstruction become noisy and fragmented. But with marmots, even if 98% of measurements are masked, the recovered shape remains nearly as clean and complete. So with this encoder, we can now do videography. For high frame rate capture, we can only scan a very small numbers of scanning points on the reservoir. But it is fine with a pre-trained encoder available. We call this video foundation model transit. So however, there is one more issue. The Garvin nometer cannot jump instantly between wall points. Rather, the scanning effectively sweep along a short path during each measurement. So this creates fast scan distortion. We need to explicitly model these physical distortions. So in transit, a shell's compression module first compresses the temporal dimensions and extracts the per frame features. Then feature fusion combines the current feature with the motion differences from the previous frame. The VIT blocks then model the spatial temporal structure. So by the way, one limitation we observed is that hardware response, noise, and material mismatch can shift the transient distortion and affects the reconstruction significantly. So the final sparse end-loss scenario is the holistic 3D shape recovery. Imagine we scan a 3D object, the front with the TOF and the back face with the end-loss transient. As the object itself blocks many scanning points, the end-loss measurements would be inherently sparse and irregular. So we instead use the front scan as priors to guide the back face reconstruction. We call this framework Holly 1, 2, 3. Specifically, it uses a neural RGBT fuse to unify loss radiance and end-loss transient information and results to a generative pipeline. In fact, we can simply replace the front scan with a 2D image using our claw generator to combine with the Holly 1, 2, 3 for complete 3D shape generation. So soon we will be able to conduct this on the mobile phone. The hologram of imaging is to capture the complete light transpose, and end-loss is just part of this. So recovering the full plane optic light transpose requires an incredibly high dimensional spatial space. So our idea is to combine generative priors with physical constraints to reduce the samples. In short, this is an imager, but with generative reconstruction. So at the upcoming SIGGRAPH, we will present this new imaging technology called the GenPi. So we start by measuring the point clouds of the scene and use a 3D foundation model to complete a geometry. To measure the light transpose is physically consistent with measurements, we apply differentiable transient path tracing. So this enforces the generation physically consistent with the actual measurements. So hardware-wise, we have designed a scanning system to simultaneously support lighting and imaging. We first coupled the laser into a fiber and put several collimators at different locations in the system. So we put the collimator behind the splitter, and we form a confocal TOF scanner. Also, putting the collimator behind a diffuser or directing it towards a reflective diffuse, we create the light sources. So we also introduce additional composition modules to handle the misalignments. Details can be found in the paper that we will present at SIGGRAPH next week. So our solution allows for per pixel and per frame light transport recovery. At any timestamp, we can determine exactly what percentage of the captured photons belongs to the first bounce and higher order reflections. So here, different colors show different bounces. So we can also play the transient video and label different color components by different colors. In the first scene, we see the light transpose between the surface of the apple and the ground. So for more specular case, the visualization shows lots more inter-reflection within the scenes. So we can further conduct time on warp, meaning removing the propagation delay from the scene surface to sensor to recover a physically correct light propagation video. We can further conduct time-resolved relighting. Since we have the reconstructed materials and geometry, we can add the new structures lights, which is in the upper video, or the normal point light source, which is in the bottom one, so into the scene to visualize their time-resolved propagation. So now I'd like to conclude. Vincent's recent article actually has attracted a lot of attention in China. His argument is that 3D vision tasks are now being replaced by a single end-to-end model. So my talk has shown in that it may be happening to imaging as well. But is it really so? So today, one can easily generate a 3D scene using like the ChatGPT or the Gemini, or Nano Banana, like these we have shown in these slides. But no technology today can generate a massive 3D scene as you see in these slides. And then we're going to asking the question, why? So there are actually many reasons, but one of them is a lack of physics. A real messy scene should be messy, but physically correct. The Fermat's formula, which received the honorable mention last night and presented this morning, is a step forward to handle physics. But there is more. So what is physics anyway? Physics reflects the relations between entities. In fact, relations can go beyond physics. They can reflect culture, identity, and even power relations. As last year's SIGGRAPH, we point out that it is essential to capture relations. So at first, we thought LLMs can capture relations of objects in an image. But very quickly, we realized that these relations are not enough. For example, what we mean by on, off, sides, they are vague prepositions. We need a better vision language model to describe those relations. So in CAST, we resort to graphs and physical simulations. It is quite effective with more ongoing developments. Okay, but how about capturing the relationship directly? Isn't light transport exactly a way to capture relation? With advance on representation and generation. So this is what Jingyi believes the next step of imaging, the spatial relation imaging. Okay, that concludes my talk. And Jingyi wants to emphasize that he really wants to give this talk by himself. He has spent weeks preparing the talk. He also extends the warmest welcome and invitation to everyone in this room to Shanghai Tech. And thank you.
Thank you, Nianyi. I guess you are not taking questions. So we can move to the next talk, but definitely we will send our message to Jingyi as well. Okay, so the next talk, showing up. Where is it? Okay, yes. So the next talk will be the ICCP paper, like Handler fiber layer polarizance enabled pupil detection for eye tracking. So the speaker is Gretchen Velasco. Let's welcome the speaker.
Hi, my name is Gretchen, and I'm here presenting on Henle fiber layer polarizance-enabled pupil detection for eye tracking. I know it's a big mouthful. Before we get into it, I really want to put this in the back of your minds, my main research goal for this project. So I really want to develop an optics-based pupil detection method that is compatible in near-eye operations, really ideally to work in wearables or in a goggle format, but also have low computational complexity, so it can operate in real time with limited computational resources. So with this in mind, let's take a look at what's already out there with eye tracking. So the PCCR method is a well-studied method for eye tracking. It's used in most commercially available eye trackers today. It works simply by finding the pupil center and using one or more corneal reflections, but also called glints, to form a pupil glint vector. And then from that computed pupil glint vector, you can estimate gaze. Locating the glint is a well-solved problem. You can either do it with thresholding or local maximas. However, finding the pupil is a bit more difficult. You can split up the two main methods of pupil detection, either using shape-based methods or optics-based methods. So these methods are well studied, but they do each have their own limitations. In shape-based, you can have traditional image processing techniques, which are generally not as robust, especially with varying illumination conditions. And then we have learning-based methods, which have increased robustness, increased accuracy, but you have to deal with it being computationally expensive. Optics-based methods are usually depend on the modulation of light. So one popular method is the bright-dark pupil effect. If anyone knows the red-eye effect, it's essentially the same thing. You have one LED that's on axis with the camera and one off axis with the camera, and you alternate between the two. So you have a flooded image of the pupil and then completely darkened. And it works great for distance trackers. However, once you start bringing that illumination source closer and closer and closer to the face, it illuminates not only your eye, but everything else around it. So it makes imaging it a little bit more difficult. So recent works have actually looked into using polarization to enhance eye tracking features. A lot of these works focus on the inherent polarization properties of things outside of your eye, such as the iris and the cornea. However, our work will only focus on the Henle fiber layer. The Henle fiber layer is located at the very back of your eye at the retina. You have a very nice little sandwich of collagen fibers, and the Henle fiber layer has a bifurcant property just due to its very dense and ordered structure. And for those who are unfamiliar, bifurcance is essentially an optical property of a material where the refractive index depends on the polarization direction of the light relative to the surface normal. And the use of the Henle fiber layer's bifurcance property is actually well documented in medical literature and is well utilized in diagnostic imaging. So this leads us to the question. I didn't mean to do that. So this leads us to the question is, how can we take advantage of these properties for pupil tracking and pupil detection? So to figure this out, we did a little bit of an experiment. So here we have a polarized illumination source and a polarization camera. And what we see here is the surrounding features are moderately suppressed, but we have this spatially varying pattern on the iris. And the pupil has some signal, but it's not as good. And counterintuitively, using unpolarized illumination gives you a very good, dense signal at the pupil, while everything else is suppressed. And that left me with a question: why is this the case? Typically, if you want to strengthen polarized signal, you just throw polarized illumination at it. So before we can answer that question, I think we have to go back to the basics. So to start, Stokes parameters are used to describe polarization states of light. Each are defined as a linear combination of the measurements of a rotating analyzer. So I0, I45, I90, I35 for a typical polarization camera. So as a visual aid, I included some images of what each Stokes parameter would look like. So here S0 is essentially just intensity. It's an intensity image. And here are your vertical and horizontal components of polarization. And these intensities shows where those components are the strongest. And here is circular polarization. That requires a quarter wave plate to image, and generally that signal is pretty weak. Additionally, we use Stokes parameters to get key metrics like magnitude, which is DOLP, degree of linear polarization, which just tells us how polarized that light is. So when DOLP is 0, the light is completely unpolarized. And when the DOLP is 1, DOLP 0 is complete unpolarized, and when the DOLP is 1, means it's completely polarized. Anywhere in between means it's partially polarized. And then angle of linear polarization just tells us the orientation. So what direction is the polarized light? So now that we know how to describe this polarization state of light, how can we model how polarized light interacts with an object? And that is done with Mueller matrices. So within a Mueller matrix, we have a bunch of different properties. So here we have total intensity, which is intensity, like a normal intensity image. And dye attenuation is simply intensity that is dependent on the input state of the polarization state. It's just, dye attenuation is essentially intensity that just depends on the input polarization state of the light. And next we have polarizance, which is the tendency for polarized light to become polarized. Wait, no. It's a tendency for polarized light to become transmitted under an unpolarized incident. And then next we have retardance, which is a polarization-dependent phase change. So if you have access to a Mueller matrix, it's pretty easy to be able to characterize these eye features. So up here we have 3 histograms of one retardance, polarizance, and then linear polarizance, which we'll get to later. And from these histograms that we can see, we did per pixel ROI for different regions of the eye, so the sclera, the iris, and the surrounding features like any skin and hair. And we found that the pupil has a very strong polarizance and weak retardance, and the iris has very strong retardance, well, slightly weaker polarizance. And then we went further to see if we go and we threshold through those intensities, we found that it's way easier to actually isolate the pupil using polarizance and linear polarizance compared to polarized illumination, which is going to be retardance. So then there comes the matter of, well, how do you measure polarizance? Well, polarizance lives in this portion of the Mueller matrix. So typically you can just compute it by taking a combination of the elements of the first column. But then we kind of run into a problem here. Measuring Mueller matrices is actually really difficult, and especially with non-stationary specimens like human eyes. It can be very difficult and time-consuming, and you can run into a lot of noise and a lot of motion artifacts. So what else can we do about it? So, all right, if we don't have access to a Mueller matrix, can we still measure polarizance? Well, the answer is yes, if you assume unpolarized illumination. Because essentially polarizance under an unpolarized source just becomes an equivalent to dope and degree of polarization, dope. And that means we can just use a regular polarization camera just to measure those parameters. So to measure this, we made a very simple setup, actually. So we used a polarization camera, which had a sensor size of 248 by 2048, which is going to be a 5 megapixel camera. And we had just NIR LEDs as illumination source. And we had an additional optical rest just to make sure that people's heads were relatively stationary while we were collecting data. And we did a small data collection with just 10 volunteers, 8 male, 2 females. Some were wearing contact lenses, some weren't. And we tried to vary the eye colors as much as we can, but with such a small sample, you don't get that much. And for the purposes of benchmarking, from the intensity image, we drew an ellipse around the pupil and marked the pupil center. And then for the glints, we just marked the specular reflections from the LEDs. And since, I missed the water. So sorry. Since the optics kind of just did most of the work, the post-processing actually becomes quite simple. From the polarization camera, you get the linear analyzer images. So I0, I90, I45, I135. So if you notice over here, this is our estimated pupil, and then the pupil glint vector. If you pay attention, you might see some misestimations of the actual pupil size, and that's usually due to occlusion of the pupil. And that's really, almost every eye tracking algorithm that depends on finding the pupil will have that problem, because you just can't prevent people from blinking. So what ends up with happening with our method is that we can still effectively detect the pupil, and we'll have a nice pupil mask, but it becomes a difficult problem trying to effectively determine the center of that pupil relative to that kind of like half circle. And for our performance evaluation, we had a bit of trouble trying to find different methods to benchmark with, but we ended up finding one and it worked out pretty well. So we just compared the detected pupil and the pupil center, and we computed the mean and median error between the detected and annotated pupil centers, and we also compared the mean and median intersection over union of the binary pupil masks. And for both the mean and median, we outperformed them. We were able to create more accurate masks. AreaSAM performed slightly better when comparing the mean error, but when removing all of the outliers, we actually got a significant advantage in the median error for the pupil center. But I think one of the most important things you can look at is the difference in execution time. So on a 5 megapixel image, we were able to operate at 68 frames per second on the CPU and 108 frames per second on a GPU, which compared to 2.5 frames per second on a GPU is miles ahead. And this is still on the 5 megapixel image. If we're able to scale down the image, we can operate much faster. So in conclusion, we demonstrated that linear polarizance is actually a really strong discriminating feature for pupil detection that's been a bit overlooked. And we developed an optics-based pupil detection technique that's compatible with goggles and near-eye operation. And the proposed light-mate robust pupil detection algorithm just based on thresholding the polarizance measurements. And we were able to operate at 109 frames per second inference rate with a 5 megapixel detector. And most of our future work will focus on doing larger scales experiments and then scaling down our design to work in a goggle prototype. And that's it. Do you have any questions?
Thank you. So now we have time for maybe one question. Any question from the audience? Over there.
Hi, great talk. So right here on your right.
Oh my God, I'm so sorry.
So you showed also the angle of polarization, and it looked quite like all random. So was there a reason why when you have one polarized light coming in, you get like random polarization angles? And is there a way to use the angle of polarization as well, apart from the degree for this?
Honestly, no, because there wasn't very much consistency with the angle, but we have a lot more consistency with dope. I think it's just a matter of how much light intensity that we're receiving back, and an angle of polarization has nothing to do with that.
Do you also test out with different eye colors? Like with different eye colors, do you see different DOLP, and does the accuracy change?
Okay. Yes. So most of our subjects had brown eyes, but we had a couple with like blue eyes, and it performed about the same. In further experiments, we want to really expand the number of eye colors that we include in our study. Right.
Great. Thank you so much. Let's send the speaker again. Thank you. Okay, 2 more talks. Stay tuned. Lunch is coming soon. So the next one, we have the spatial polarization multiplexing, single shot invisible shape and reflectance recovery. The speaker is Tomoki Ichikawa. Let's welcome.
Hello, I am Tomoki Ichikawa. Today I present spatial polarization multiplexing, single shot invisible shape and reflectance recovery, working with Ryo Kawahara and Konishino at Kyoto University Computer Vision Lab. Shape and reflectance sensing have long been fundamental research topics in computer vision, as they play a key role in many applications, such as computer graphics and robotics. Despite the emergence of inference models based on land priors, these direct measurement remains essential for acquiring reliable data, especially for unseen targets. By projecting different illumination patterns that encode geometric and radiometric cues, we can recover both shape and reflectance. But this approach has two limitations. First, the target scene must remain static because it requires multiple shots. Second, the projected light pattern disturbs human visual perception, as seen in this slide. These lead us to the central questions. Can we sense both shape and reflectance in a single shot without being noticed? If so, we can apply shape and reflectance sensing to applications with dynamic human-object interaction, such as cooking scenes and XR experience. Single-shot joint sensing of shape and reflectance is a challenging problem. In shape sensing, the projected pattern inevitably alters the appearance of the object. This appearance change not only disturbs human visual perception, but also entangles the object texture and the projected pattern, making reliable reflectance acquisition difficult. In addition, reflectance acquisition itself usually requires multiple illumination settings because the diffuse color and the specular diffuse color needs to be disentangled from the specular highlight. In this work, we achieve shape and reflectance recovery from a single shot. The key idea is to project the invisible spatially multiplexed polarization pattern, which we refer to as spatial polarization multiplexing. The AOP image, which indicates polarization orientation, shows the projected polarization pattern that encodes geometric cues. This spatial polarization multiplexing enables pattern decoding for shape recovery and also polarimetric decomposition for reflectance recovery from only a single polarimetric image. Why is the polarization pattern essential for single-shot joint sensing? First, the polarization is independent of light intensity. This means that the pattern can provide geometric cues without altering object appearance, which enables reliable reflectance recovery. Second, the polarimetric reflection enables decomposition of reflected light into specular and diffuse component. Specular polarization depends on incident polarization, while diffuse polarization is independent of it. By projecting different polarization states, we can separate the specular and diffuse reflections. Thanks to these advantages of the polarization pattern, our method achieves single-shot joint sensing without being noticed. Before explaining our method, let me first describe how to project a polarization pattern in practice. Such a hardware may be unfamiliar, but it can be easily built based on LCD projector. In the LCD projector, the emitted light is polarized by a polarizer and then passes through the liquid crystal spatial light modulator. The spatial light modulator rotates the polarization orientation at each pixel independently. Then the analyzer converts this rotated polarization into the intensity pattern corresponding to the input image. In fact, we already get the polarization pattern in this part. By simply removing the analyzer from the LCD projector, we can get the polarization projector, which can spatially control the AOLP of the emitted light. This is the actual hardware we use that consists of collimated polarized light source, spatial light modulator, and a convex lens. Although our previous work, Spiders, uses polarization patterns for shape and reflectance sensing, it requires multiple polarization patterns and is limited to static scenes. In contrast, in this work, our method enables single-shot sensing and dynamic surface reconstruction with a novel polarization pattern. We design a striped polarization pattern with quantized AOP values for single-shot and reflectance sensing. This pattern is projected from the polarization projector, and the polarimeter camera captures the reflected polarization pattern in a single shot. A stripe pattern can be decoded by comparing the stripe line sequences before and after reflection for triangulation. For BRDF estimation, our method decomposes the captured parametric image into parametric specular and parametric diffuse reflections. In general, this decomposition requires multiple projections with different polarization states. In contrast, our method achieves it in a single shot by spatially multiplexing different polarization states in neighboring pixels. By using decomposed reflections and reconstructed shape, we then estimate the BRDF parameters. To enable these decoding and parametric decomposition, our stripe polarization pattern should satisfy two requirements. First, each sub-pattern should appear only once. This pattern guarantees unique pattern decoding because each detected sub-patterns uniquely determine its correspondence of the projected pattern. Now, a Dubran sequence is suitable for this purpose. In a Dubran sequence, every possible substrings of the given length appears exactly once. For example, this sequence is one of the Dubran sequences in which all two length substrings appear exactly once. The second requirement is that the adjacent polarization states should be clearly distinguished and sufficiently varied. If the adjacent polarization states are the same or too similar, each stripe pattern becomes unclear, making pattern detection and decoding difficult. In addition, sufficient variation in the polarization states is needed for parametric decomposition. To satisfy this, we remove unsuitable subpatterns from the Dubran sequence. Our polarization pattern is generated by assigning quantized AOP values to a constrained Dubran sequence. Following the requirements, we impose two constraints on subpatterns to increase the separation between neighboring AOP values. First, adjacent lines should be adjacent lines should have an AOP difference of at least two quantization steps, so that neighboring lines can be clearly distinguished. Second, the AOP values of any three sequential lines should be different, ensuring sufficient variation in the polarization states for parametric decomposition. The observed polarization pattern differs from the projected pattern due to the reflection on the surface. To robustly detect and decode the polarization pattern under this modulation, our method quantizes the observed AOLP values for detection. Quantization makes the pattern detection robust to small AOP modulation, but it cannot handle larger modulations than the quantization step. To address this, we use dynamic programming to perform robust matching between the projected and detected line sequences by globally maximizing matching score. Here are the results of pattern decoding. Although the pattern detection based on the AOLP quantization causes some detection errors, dynamic programming-based decoding corrects these errors for accurate shape reconstruction. We experimentally validate our single-shot method on various real-world objects. Here are the reconstruction results and the rewriting results. Our method accurately reconstructs both shape and reflectance, including color texture, from a single shot, while preserving the object natural appearance. Here are more shape reconstruction and rewriting results for real-world objects with different shapes and materials. Our method can also reconstruct the dynamic surface from each frame of a continuous parametric sequence. The reconstructed shape and reflectance enables rewriting of the surface at each frame. The surface normal and rewriting results accurately capture the surface deformation as it is pushed by a finger. These are the reconstruction results for fake blade loaf expanding after compression. The reconstructed shape and albedo accurately follow the surface deformation. And these are the reconstruction results for waving cross. The reconstructed shape accurately captures the dynamic wrinkle deformation. At the same time, the color texture is captured without interference of the projected pattern. Single-shot reconstruction is suitable for dynamic objects, but its reconstruction resolution is limited by stripe line widths. In real-world scenes, we often observe the dynamic and static object at the same time. Thus, using only a single pattern with multi-frame information in static regions, where different patterns can be projected for accurate and detailed reconstruction. To fully take advantage of multiple shots for static objects, we use smoothed and shifted polarization patterns. These patterns provide per pixel correspondences for high-resolution reconstruction of static regions. At the same time, each pattern can be decoded independently for single-shot reconstruction of dynamic regions. Since the polarization pattern does not affect the object appearance, we can automatically detect the dynamic regions based on the intensity changes. These are the results of high-resolution reconstruction for static objects. Our multi-pattern method captures detailed surface texture. Shifted patterns allow our method to adapt the reconstruction resolution based on object motion. The static clay figure is reconstructed at high resolution, while the moving lava duck is reconstructed at lower resolution from individual frames. After the lava duck stops moving, it is also reconstructed at high resolution, capturing detailed surface texture. Here we compare the rewriting results between dynamic and static frames of lava duck. For the static frame, the sharper color texture and detailed surface geometry around the wings are successfully recovered. This is a summary of this work. We believe that our spatial polarization multiplexing opens up a new avenue for 3D sensing, thanks to its ability to jointly recover radiometric properties, applicability to both dynamic and static scenes, and invisibility to human eyes. Thank you for listening.
Thank you. So now we have time for maybe one more question. Any over there? Thank you.
Hi, I had a question about your result videos. So in them, you don't show like the finger. For some reason, the finger disappears even if it's in front of the object. So can you explain what's going on there?
This result? And
Yeah. So like the finger is like clearly in front of the object, but the depth is like just gone.
We mask out the fingers because, in fact, our method assumes uniform material. So the finger and the this toy is different, has different materials. So we mask out this in our experiments.
Okay, thank you.
Great. So let's send the speaker again. Thank you so much.
Thank you.
Okay, so we have the last paper talk of this session, Gaussian anchors for declaration of radio devices very interesting. So the speaker is Chris Lee from Rice. Let's welcome.
Okay, good afternoon, everybody. Today I'll be presenting Gale. I'm Chris Lee. At its core, Gale is actually a method for localizing radio devices, and I think maybe it's a bit odd that we're here, but I do hope that I can motivate why it is that we're studying this problem of localization, in that localization is actually going to be a critical driver and enabler for the next generation of radio imaging applications. And I'll explain all of this just in a second. But radio frequency sensing is really a historically rich topic, with radars first being deployed in World War II en masse in airborne settings. And here we're not doing any imaging yet, right? All we're doing, these things are mounted to the front of planes, and all we're doing is this detection and ranging task. So is there something there? How far is it? What is its heading, right, is the main task of these. It's not really imaging yet. In 1951, Carl Wiley invents or proposes synthetic aperture radar. And so he says, if we fly basically as straight as possible and as level as possible, and we send out multiple radar measurements, then we record all of those, and when we land, somebody stitches all of these together into our first radio frequency images. Nowadays, radar imaging is like really widely commercialized in, if you ever take a Waymo, or your car probably has plenty of radars on board already. If you go to the airport, you're being scanned by a millimeter wave scanner. And so the commercialization of these has been really driven, probably similarly to cameras, with digital backends that has been shrinking the form factor and lowering the costs, so we can actually have widely available radar imaging applications. So we have a lot of imaging applications at RF. It's also detecting the rain for your weather reports and these sort of things. So the question that our group and a lot of people in the wireless space are asking is, what is the next big opportunity for RF sensing and imaging specifically, right? So all of these systems have fixed apertures, right? Either mechanical scanning or fixed antenna patterns on their chips. And so barring just increasing the size of these systems, like how do we actually push the resolution? How do we develop new systems with improved resolutions? And what this basically amounts to is, where can we get higher bandwidths and larger aperture sizes? And so where myself and a lot of players in the wireless space are actually looking to is this idea of using the network itself as a sensor. And so if we have 200 people in this room, then we have 200 different smartphones, right? We have cars that are driving around through natural motion. And so can we use kind of all of these devices networked together, right, across natural motion, you walking down the street, my car taking a right turn, to synthesize a city-wide aperture, right? So we have a lot of different carriers and a lot of natural motion that can help us perform really, really large aperture imaging. There is so much research to do in this area, and I myself am only studying one small part of this. One thing is, how do you actually synchronize all of these devices to transmit and receive simultaneously while not interfering with each other? So a lot of scheduling problems here. And what the study of my research is now we don't have fixed apertures anymore, right? We have dynamic apertures from people moving, people being introduced to the aperture, people exiting the aperture. And so if we want to do imaging with these new dynamic apertures, we actually have to localize every single one of these devices before we actually form any image. And to motivate this, what we've done is we've taken a small radar image of this foot-by-foot scene, and the top here is captured by a motorized rail, giving us micron-level precision. And we start adding in positioning error on the order of single wavelengths, right? So our radar here at Rice is at 170 gigahertz. So think about 6 millimeters of average error of my aperture. And suddenly we get all of these destructive streaking effects, right? Photography and ICCP has been completely destroyed. And if we go further with this 20 lambda, an order of magnitude more, we get complete loss of information. There's absolutely nothing that you can actually do with this image. And so the conclusion here is we need lambda order positioning. So at this carrier, it'd be millimeter order localization accuracy before we can actually cohere an aperture to do any sort of important imaging. And so what positioning systems actually exist today, and can they get us there? So we're all familiar with GPS, or at least we're all using GPS every single day. And so I want to cover the basic premise, which we all may be familiar with. So we have satellites in space. Somebody gives me their position. It's actually my cellular provider now, but somebody is giving me their position, and I'm going to measure my range to these satellites. And since I know the range to some known positions, I can perform what's called lateration, right? And so I'm measuring the range to all these satellites, but these satellites are also telling me who they are, right? So they're communicating some level of information to identify themselves. And if I identify myself, I can say range 1 corresponds to satellite 1, range 2, satellite 2. I can form an ordered set of equations, and I can solve that ordered set of equations in order to do lateration. And we have standards that actually define how do I range, how do I identify. The space concept is moving towards terrestrial networks in cellular and Wi-Fi positioning systems. The concept really is the same. The sentiment is the same. I know the positions of my cell towers. I can measure the range to them, and I can perform lateration given all of these measurements. And again, here we have some identity that's being modulated over some standard like 5G or 802.11. Here we're getting more and more towards the accuracies that maybe we need. Now we're getting to decimeter order, due to the fact that we're kind of moving in towards Earth, but we're still not there to the millimeter that I need. Right? More recently, what we have in the last decade or so is this idea that I can actually use my sensing signal itself. So if I'm at millimeter wave, then I can deploy these basically smart RFID tags. And you can kind of think of these tags as relay walls with some modulated phase mask, I guess, in your terms, right? So what these things are doing is I send out a sensing signal, it retroreflects back, and it's going to modulate that retroreflection in some way. And in doing so, I get the same exact measurements that I would from all of these other systems, just with much higher ranging resolution, right? So I have range 1 to tag 1, right? And it's going to modulate some identity on top of it. And so here we're getting to millimeter accuracy. So the results here are fantastic that we have these millimeter accuracies. However, all of these systems I've kind of hit over and over on this idea of identity, right? The fact that all of these systems are modulating data through identity in some way. And if we think about what that identification actually entails, right? If I require identification, this is saying is that I'm actually modulating some sort of data onto my waveform that I'm either sending down or retroreflecting. Right? And what this requires is that whenever you have modulated data, you need to standardize what is the carrier, right? What is the carrier frequency, what is the bandwidth, and what is the waveform that I'm actually using in order to modulate that data. Going down this line of thinking, this requires that all of my sensors that are using whatever set of infrastructure I deploy actually has a standardized demodulation pipeline, right? In a world where startups are releasing new radars at new waveforms and new carriers every couple months, right? It's pretty untenable for me to assume that they can also they can design their own infrastructure and deploy it widely so that they can actually do localization for themselves, right? And so the guiding question of Gale is, can we remove the requirement for identification in a lateration formulation? So all lateration formulations kind of previously suppose that I have this identity and ordering associated with it. Can I actually remove that assumption? And the kind of representative example of infrastructure that does not have any identity associated with it is kind of just pieces of metal, right? So and on the left here, I have a metal corner cube. It's just aluminum foil or a steel ball bearing, right? And clearly what we have is really simple infrastructure, and there's no hardware attached to this. It's not doing any structured modulation or anything in order to actually give you identity, right? However, what it is doing is giving you really, really strong reflections across a really, really wide bandwidth that I would care about. So from 30 to 300 gigahertz, kind of the current radio spectrum. Clearly, these are all standard agnostic, right? There's no standardization of the modulation that's happening here. The problem that comes with using these as infrastructure is that suddenly their reflections are now really ambiguous among the scene, right? So if I measure this gray line, which is a range profile, it's the kind of native domain of radars, are these peaks coming from my anchors, or are they coming from other stuff in my scene, like this couch or like my lamp, right? And so this is what the problem that Gale is facing, right? Is if I have these set of peaks, right? I know that some of them came from the anchors, and I know what these anchor positions are, right? But how do I still perform lateration in this case, right? One naive approach is I could just assume that the top 3 peaks in this are the anchors. I can assign them to anchor positions, right? And then I can do lateration, but this really is problematic whenever I have other strong reflections in the scene that I don't know, right? And so what we're proposing is this idea of Gaussian anchors, right? And so we're borrowing concepts from computer vision and scene representations in order to actually solve this problem. So we represent every anchor position as a 3D Gaussian volume, right? And instead of doing what is classical, a 3D to 2D RGB projection, instead we project or splat into the 1D range domain, right? And the insight here is that if in the top right, if my initial estimate of the position is incorrect and I splat my Gaussians into the range domain, then the peaks here do not align with peaks in my measurement, right? With the peaks actually in my measurement. If I do refine my position, if I have an actually close estimate to my true position, then suddenly we get structural alignment between my rendered peaks here in blue and my measurement in gray. And so we use this insight in order to pose a continuous optimization problem, with the loss being kind of the structural difference between the rendered peaks in blue and the measurement, right? So now we're ready to just kind of go through the whole pipeline. So again, we have a measurement, right? So we have my radio that's sending stuff out. These reflections are bounced off of the anchors and other stuff in the scene, and I kind of get this ambiguous gray line. Some of these peaks are the anchors, which ones I don't know yet, right? On my synthesis side, what I have is an estimate of my radar position and a bunch of parameters that define the anchors. So this is like covariance, kind of spherical harmonic coefficients. And what I can do is I can splat this into the 1D range domain. I can take a loss, right? And this loss that we are is basically, a correlation, right? So maximize the correlation between these, the splatted range profile and the measurement range profile. And we also put a regularization on the volume of my 3D Gaussian so that we kind of encourage these things to shrink to a point to give us really fine localization accuracy. And this is what this looks like. So we have these Gaussians initially that are very wide, and they're shifting and narrowing so that we actually align with the peaks in my measurement. And in doing so, this is what we mean when we say we implicitly solve for the position rather than kind of explicitly stating that measurements ranges are associated with anchor positions. I'll let this converge before we move on. Okay, so we tested Gale on the experimental radar system we have at Rice. So this radar operates at 170 to 260 gigahertz. And what we do is we place 4 of these known anchors in the scene. So we know these positions of these corner reflectors, and we move our radar to 400 different positions. And then we put some other stuff in the scene. So we have an owl or some X-Acto knife, right? And we measure this quantity. What is the anchor to scene ratio, which is basically just a power ratio between the anchors, my 4 anchors, and the stuff that I put in my scene, right? And so the ground truth that we'll compare against is this motorized rail output, right? So as input to Gale, we add a bunch of random noise to the rail positions, and then we estimate from there. And so in the case that my ASR is infinite, basically I didn't put anything in my scene, right? Then what I said earlier, which is you can just pick, the 4 top peaks in your scene, associate them with the anchor positions, and then do a traditional lateration formulation. This still works, right? So you can see that kind of way of thinking can still get you to this wavelength order accuracy. So this is, about 2 millimeters of accuracy that we're getting in for a traditional formulation. But as soon as you start adding stuff into your scene, so we have like a metal circuit board, or we have the blade of this X-Acto knife, then suddenly a traditional formulation gets confounded by other stuff in the scene. So my knife at certain positions, because it is a specular object at radio frequencies, produces reflections that are actually stronger than my anchors. And so if I associate those, then I'm going to make mistakes, right? Meanwhile, since Gale takes a continuous loss, or is continuously optimizing over the loss over an entire range profile, we can still get consistent performance. So we can still get consistent 2 millimeter lambda ordered performance. And so what does this mean? So we take all of these positions, localize them to synthesize an aperture, and then we start forming images, right? So the baseline here that is kind of the old way of thinking. We get a lot of these streaking artifacts that happen due to misplaced radar positions, while we are recovering pretty faithfully the visual effects that we have here, like the eyes of the owl or the handle of my X-Acto knife. And so what we're kind of showing here is that we have since we're getting wavelength order localization, we can effectively cohere a synthetic aperture. We also kind of test how close are we to actually the theoretical resolution limit, and so we use different anchors here, some steel ball bearings, and we actually measure what is the PSF and MTF of my aperture that I'm cohering with Gale versus the ground truth, and we get very, very close alignments with the 2D PSFs and contrast in both the downrange and cross-range directions. So to conclude what we've done, what Gale's kind of way of doing things is moving away from traditionally, a lot of complexity has lied at the infrastructure. So if you think about satellites being $1 billion, my cell phone or my cell tower being a couple $1 million, right? We have 1 cent worth of hardware at our infrastructure, and yet we can still perform this level of localization, even though we're not kind of presupposing a certain waveform, a certain carrier, any standardization, right? And so in achieving this level of accuracy, we're hoping that we can enable a whole other set of RF imaging applications from natural motion. And so there's still a ton of research to do, and we're doing more measurements every day. And so this is me. We've bought a bunch of TI radars, and we've mounted them all sorts of places, right? So we have one handheld setup. We mounted one on another rail. And so what we're getting to is moving towards really in the wild scenarios. So my goal is to be able to scan this room with the radar with my hand, localize all of those positions, and then cohere a really, really nice room scale image. And also my colleagues, which I'm sure you'll see their work soon, is developing really high resolution multimodal systems. And so what I'm looking to do is maybe not presuppose we know anchor positions, but map them previously with some other system and then apply our Gale framework to actually perform some of these in the wild localization results. So with that, thank you very much. I have great collaborators. I'm sure you know some of them. And so with that, thank you, and you can contact me here.
Thank you. Okay, so questions. Very interesting talk. Any questions from the audience over there?
Hi, great talk. So I have 2 little questions. One is, can you explain a bit about the electrical engineering setup you used for your experiments? And have you tested for longer range localization?
Yeah, so the first thing is you're wondering about the radar setup, right? I do have one slide. I personally did not, so Maxcentric is on here, and they're the actual designers of the slides, or designer of the radar. This thing operates in stepped frequency continuous wave. So instead of maybe FMCW, in order to be able to get 170 to 260 gigahertz, we need to limit the instantaneous bandwidth. So if you think the frequency time looks like this, right? And the way that they do this is this set of hardware, right?
So you're not showing it to them.
Oh. Hide this. Yeah, I think this is a hidden slide. Okay. Yeah, this one. So we have a step frequency setup instead of like a continuous wave setup. And then your second question was about range. And so that's what we're getting to. The reason we have like kind of a foot-by-foot scene is because of the beam width of my radar. That maximum range of the radar is 20 meters, something like that. We expect that it should work, and we have some simulation results in the paper that kind of take into account path loss, and these things are built in ray tracers, so I think that would be of interest to you. Yeah, this thing does generalize to long ranges, I would expect.
Great, so we can continue the discussion over lunch because we don't want to delay the lunch time. Let's thank the speaker again. Thank you.